We've already talked about how the electric field integrated along any path between 2 points A and B can give you the electric potential difference between those 2 points. If you want the non-calculus definition, then it's just the negative of the electric field dotted with the displacement vector between those 2 points will give you the change in electric potential. But remember, this only works if the electric field is constant. This sort of brings us to one thing that I wanted to discuss in the previous video, but left off for this video, and that's the idea of constant electric potential. We talked about how electric fields can be constant before. We call them uniform electric fields when the electric field is constant everywhere. But the electric potential can also be constant in certain regions of space. When the electric potential is constant between 2 points, then that's the same as saying delta V is 0 between these 2 points, because delta V is VB minus VA. For example, consider the situation where we have a uniform electric field in the horizontal direction. What might the lines of constant electric potential look like? We remember from a previous video that the electric potential is constant as long as we're moving along a path that's always perpendicular to the electric field. In the case of electric fields that have a radial pattern, the electric potential is constant along concentric circles centered about the radial pattern. These circular curves that we've drawn here are called equipotential lines. The naming is quite convenient. Equi just means equal here, so it's like saying these are lines of equal potential, which is exactly what they are. The potential is equal anywhere along these curves. Now, what might the equipotential lines look like in this situation? In order to always remain perpendicular to the electric field, the equipotential lines here are just vertical lines. It's not too hard to see that as long as the line is vertical, it's always perpendicular to the electric field, which is always horizontal. So if we're using the non-calculus definition, then we remember that the potential difference is given by negative E dot S. If the angle between E and the displacement line is theta, then this is negative ES cosine of theta. Then the magnitude of the electric field between 2 points in space here is given by the negative potential difference between those 2 points divided by the distance between those 2 points that's in the direction of the electric field. This looks like S cosine of theta for that distance specifically. It kind of makes sense because we remember that if we travel perpendicular to the electric field, then the electric potential doesn't change. So it's really like for any 2 points we choose here, we can go parallel to the electric field and perpendicular to the electric field, and only one of those movements will contribute to the actual potential difference. Moving in the perpendicular direction leads to a zero potential difference. So that's a way of looking at the uniform electric field, but frequently electric fields are varying throughout space, so the result of that is we have to evaluate an integral if we care about the change in potential between 2 points. Now, just want to put out a warning that the rest of this video is completely calculus based, so feel free to stick around if you like, but we're not going to go over any non-calculus stuff. Really, this integral here is just the integral of dV along this path. We can say dV, the differential change in electric potential, is just the negative of the electric field dotted with ds for some really small ds. In that case, if we care about the electric field in the direction of ds, then the electric field component is given by the negative derivative of v with respect to s. The math is a bit sloppy, but there it is. This presumes that you kind of already know the potential as a function of s too, but sometimes that's not always the case. What we might have is the electric potential as a function of x, y, and z. This is a sort of general electric potential function of any point in space. So then a more advanced and general definition for the electric field due to any potential that's a function of x, y, and z like this would involve evaluating this thing called the partial derivative of the electric field with respect to x, if you want the component of the electric field in the x direction, the partial derivative with respect to y if you want the component in the y direction, and the partial derivative with respect to z if you want the component of the electric field in the z direction. So what is this partial derivative thingy? It looks like quite a complicated concept, maybe you've never seen it before, but really it's even easier than taking a normal derivative. All you have to do is just imagine the other two variables are constants, and then proceed to take a normal derivative that way. Let's try an example. Imagine if you had this electric potential in space, V equals 3 times x plus 5 times z. I'm just going to be sloppy with the units here, but you could imagine maybe V was in volts and E was in newtons per coulomb, for instance. Trying to keep a bunch of units floating around might just make things too confusing, so we're going to try and keep it simple. If we wanted the electric field in the x direction, all we have to do is take the partial derivative of the electric potential with respect to x. In this case, the x component of the electric field is just -3. Remember, y and z we're just treating as constants, so when you differentiate a constant, the term just goes to 0. And all we're left with is this 3. The electric field component in the y direction would be given by the partial derivative with respect to y. This would just be 0 because we're treating x and z as constants here, but y as variable. So the derivative of a bunch of constants added together is just 0. Finally, if we want the electric field component in the z direction, all we have to do is evaluate the partial derivative of the expression with respect to z. Treating x and y as constant, the partial derivative comes out to -5. And from the expression for potential, we have now deduced a general expression for the electric field at any point in space. Again, this is more of an advanced concept, so what we have here is maybe just a taste for it. Really, in intro physics problems, it's common to know or care about the electric potential as a function of a single distance, usually a radial distance. So just differentiating the potential with respect to the displacement in that direction will give us the electric field component in that direction too, which is usually all we care about also. And that's kind of all there is to it.